video, we'll be designing filters with the help of FDAtool. FDA stands for Filter Design and Analysis Graphical User Interface. It is a powerful user interface for designing and analyzing filters. FDAtool enables us to quickly design digital FIR or IAR filters by just giving the filter performance specifications or by directly specifying filter coefficients. FDAtool also provides tools for analyzing filters such as magnitude and phase response plots as well as pole zero plots. It is a convenient alternative to the command line filter design functions. In this video, we'll see how to start with FDAtool and we'll try to design a simple filter. We'll be transforming a filter from low pass to any other filter like high pass or band pass, and we'll see how do we quantize the filter so that we can reduce the area it is used to store. How do we realize the model of the filter which we have designed, and we can also edit the filter response by editing its poles and zeros. At the end, we'll see how to generate the verilog code. First, to open the filter design, we have to type FDAtool in the MATLAB. Then a window pops up in this way. We'll see how it is done practically. We type FDAtool, then a window pops up. This is the FDAtool. The first block is the current filter information, second is the filter specifications, third is the design panel. Current filter information block in the upper left displays filter properties such as filter structure, order, whether the filter is stable or not, and the source of the filter. It has a filter manager in which we can work with multiple filters at a time. Coming to filter specifications block or the filter display panel, in the upper left displays various filter responses such as magnitude. This is we can display many responses like magnitude plot, phase plot, group delay, phase delay, pole zero plot, or we can also get the coefficients of the filter. And coming to the design panel at the bottom is where you define your filter specifications. It controls what is displayed in the other two regions. Other panels can be displayed in the lower half by using sidebar buttons. We'll be seeing all these buttons in the coming video. Now next we'll see how to design a filter. We'll take a small example. We will design a low pass filter that passes all frequencies less than or equal to 20% of the Nyquist frequency, that is half the sampling frequency, and attenuates frequencies greater than or equal to 50% of Nyquist frequency. As we are taking in the form of 20% and 50% of Nyquist frequencies, here we are going to normalize the plot from 0 to 1. 20% of 0 will be the 0 frequency and 1 will have the Nyquist frequency. So 20% of Nyquist frequency will be 0.2 and 50% of Nyquist frequency will be 0.5. So here we can see the passband frequency will be 0.2 because we have to allow all that which passes below 20% of Nyquist frequency, and stop band frequency will be 0.5 because we have to attenuate all the components which are passing about 50% of Nyquist frequency. And we will design a FIR equi-ripple filter with passband attenuation of 1 dB and stop band attenuation of 80 dB. We'll see it over here. First, we have the response type. We can select whether it's low pass, high pass, band pass or stop pass, band stop. Here, as we are designing low pass filter, we select low pass. And in the design method, we decided to design an FIR equi-ripple filter. So we select FIR and we select equi-ripple from this pop-out menu. And coming to the filter order, we have two. We can specify the order of the filter which we want, or we can keep it as minimum order. If we keep it in minimum order, FDAtool directly it designs with the minimum order possible, which meets the specifications. Here we'll see how to specify the order. If we click on specifying order, Then we can enter 30, and density factor option, this controls the density of the frequency grid. Increasing the value creates a filter which more closely approximates an ideal equiripple filter, but more time is required as computation increases. So we'll leave this as 20, which is the most optimal value. Then coming to frequency specifications, as we have discussed that we are going to keep it normalized from 0 to 1. And W pass, we just now noticed that it is 0.2, which is 20% of Nyquist frequency, and W stop is 0.5. And coming to W pass and W stop, we keep it as 1 and 1, and we click on design filter. So this is an FIR filter which we have designed, which has equiripples in the stop band. Now we'll see this is the magnitude response of the filter which we have designed. We can also get the phase response by clicking on this. This is the phase response of the filter which we have designed. And if you want to see them both, then we can click on the third option, which is magnitude and phase response, which displays both magnitude and phase plots simultaneously. And if you want to see the group delay response, this is the option. Phase delay is this. If you want to know the impulse response of the filter, this is the impulse response. And step response. If you want to know the pole zeros of the filter which we have designed, these are all the poles and zeros. The circle ones are the zeros and the cross ones are the poles. If you want to know the filter coefficients we have designed of the filter, then we can click on this option. These are the different views which we can see in this design panel. Now we'll again go back to magnitude response. Here it is plotting in dB. We change this to magnitude so that we can if we go to view panel, we have specification mask, which is used to compare with the design specifications which we have given. Here we see that passband frequency we gave it as 0.2, so it is not attenuating until 0.2. Stop band frequency was given as 0.5, and it is attenuating completely after 0.5. And we gave W pass and W stop as 1. These are taken care by the filter. Now we have seen this is the response which we got when we used specifying order as 30. That we have seen here, order is 30. Now we change this to minimum order, and we again click on design filter. Then we don't get an exact low pass filter which we want to design. We can check this by changing into magnitude in dB. We see that it's not completely a low pass filter because it's very much close to the specifications which we have given, and order is reduced to 60, but it is a stable and structure is the same direct form as a FIR filter. Now we have designed, whenever we want to implement our filter in hardware, we have different types of filter structures. Like in edit, we have convert structure. We can convert it to direct form FIR, direct form FIR transpose, direct form symmetric FIR. Typically, the direct form FIR transpose structure is implemented in hardware. You can use convert structure dialog box from the edit menu which was shown, and we can convert it into any of the three forms shown. Now we keep it same as direct form FIR. Now if you want to change the analysis parameters over here, like the frequency scale, that is the x-axis, and the frequency range, whether frequency scale, whether we want it as linear or logarithmic. Frequency range is from 0 to pi or 0 to 2 pi, and the number of points. As we increase the number of points, the more accurate the graph becomes, because graph is just joining of points approximately. If we want to save the values which we have to which we have changed as default, we click on save as default. Otherwise, if we want to restore the original default values, then we can click on this button and OK. Now we'll see how to transform a filter. Now you have seen that we have designed a low pass filter. Now this is the second option over here, which is the transform filter. If we click on this, we have original filter type as low pass, which we have actually designed. We can design any high pass, band pass or band stop filter also. As we have designed a low pass filter, we'll see with the low pass filter. And here the transform filter type, the filter type which we want to change. It can be anything. As we have designed a low pass filter, we'll select band pass filter and we click on transform filter. Then the low pass filter which we have designed is converted into band pass filter. Now we'll see how to quantize the filter, which is quantizing the filter is important when we want to store this filter coefficient value somewhere, because if we don't quantize, the filter coefficient length will be infinite. But if we quantize, we are limiting the filter coefficient length. Here the quotient word length. Quotient word length can be anything which we want. Here we will be specifying 20, as I want to limit the filter quotient word length to 20. After this, we apply the changes. Then we have an option called import filter from workspace. Here, as we are designing direct form FIR, we select that from the filter structure, and in the numerator we'll be entering some values of this. These are the values of low pass filter, and we click on import filter. This is the low pass filter whose filter coefficients were given in this numerator thing. Now we'll try to realize the model of this low pass filter and we'll check whether it's working properly or not. Here the fourth option is realize model. Once we click on this, we get model. Block name can be anything. We can keep it as low pass filter and we click on realize model. Here this model will be created in the new model. Now in MATLAB we click on Simulink. This is the button which is used to open Simulink. Once we open this, then here we have a filter. Now we need to give some random values and check whether this filter is meeting the specifications. The cutoff frequency of this filter in the normalized frequency panel is 0.6. Stop. Here we have realized the model of the filter which we have designed recently in FDAtool. We have given the coefficients of the filter like this. These are the filter coefficients of the filter which is having a frequency cutoff of 0.6. Now we'll see whether the frequency components input frequencies above 0.6 are getting attenuated or not. For this we need to give an input to the low pass filter. We give a random input to the low pass filter. This input can be taken from the Simulink library browser. Here we give a random input, so click random. This we add it to the untitled. We get the random number generator. We give this as input to the filter. Now again we need to have an output. We normally see the output in Simulink using scope. Here, as we need to see the frequency output, we try to take the spectrum scope. This is the spectrum scope. As we are seeing whether it's attenuated above some frequency and below some frequency, so we need to take spectrum scope. We add this, we give this as the output to the filter. Now this is a random number generator, which is a continuous signal. First we need to sample the signal by giving the sampling time. Then in the simulation we have configuration parameters. As random number is a continuous generator, it gives continuous input. We need to change that to discrete, as the digital filter which we have designed here is a discrete input filter. So we have a block named solver. This is used to change the input into discrete. Now once it is changed to discrete, the other parameters which we get are the default parameters and they get auto adjusted. After this we click apply and next OK. Now in the spectrum scope we need to buffer the input, so we click on buffer input. We specify FFT length and these are the default values which we keep it as it is. And coming to display parameters, we need to change it to persistence and apply and OK. Now we try to run this filter. We rerun it.
Start.
Here we run it again. We got an output that we need to change it to auto scale. We see that from 0 to 500, 0.6 of 500 would be somewhere around 300. Up to 300 we are getting values as it is, almost what we have sent, but after 300 it's getting attenuated. So this is the filter which we have realized and we have proved that it's working correctly. Now coming to FDAtool again. In the FDAtool we have an option called as pole zero editor. Once we click on this, we get all the poles and zeros of the filter which we have designed. This option, the first option is move pole zero. This is used to move some poles or zeros of the filter. As these two are the conjugate zeros, they move continuously. And again, we can also add some zeros or poles only in a specific and meaningful manner. We can add some zeros over here, or this I am adding randomly, so this is not supporting it. We'll again erase all this. It's becoming unstable, so we need to remove all this. We again go back. This is how we change poles and zeros of the filter which we have designed, and correspondingly the response of the filter would be changing in the display panel. We again import the filter recently before any changes. By import filter, we import it. Now we get the original filter back. Now if we want to find the power, area or delay of the filter which we have generated, then we have an option in FDAtool which is used to generate HDL or VHDL codes. In this generate HDL, we have in filter settings, we have filter target language. We can select it as verilog or VHDL. In this video, we will see how to generate verilog. And we click on generate. After this is done, in the command window, after this generation process is done, in the command window of the MATLAB, we get the modules of the filter and as well as the test bench. This is the module of the filter which we have designed. This is the verilog code which is completely given by the FDAtool. We can copy this into Xilinx and check out the power and area or delay of the filter which we have generated. And this is the test bench which is used to check whether the filter is working properly or not using some verilog softwares like Xilinx and all. So this is how we generate the verilog or VHDL code. And this is the end of the video.